Okay, so next we're going to be talking about editing explosion. And the edit distance or Levenshtein distance is a common problem that we see in early programming contests. And so our idea here is we want to be able to, instead of just calculating the edit distance between two strings, we actually want to count the number of strings that are a particular edit distance from a given string. So let's review how we calculate the edit distance. So in order to calculate the edit distance, what we do is we make a table, a two-dimensional table, and we put one string at the top and one string down the left. And we initialize the first row with just 0, 1, 2, 3, etc. And this represents the total edit distance between an empty string and the initial given string. And then we add additional rows to this table according to a simple dynamic programming algorithm. We look up and we say, what happens if we insert a new character into our given string? What happens if we delete a character from our given string? And we look diagonally to say, what happens if we change, or if the characters are actually the same, don't change the character from one string to the next. So in this case, you can see this element of the table, which is the difference between G and G, is 0. And the reason we got that is because we went diagonally. And in this case, the characters were exactly the same, so there's no difference there. Now over here, since we have the option to delete, change, or insert, we want to take the minimum of those three. So if you look at this entry here, 1, the reason that's 1 is because we actually said we can just add an R to the G, and that gives me the distance between GR and G is actually to delete the R from the GR to get the G, okay? So we can construct this table row by row, and it gives me an ON squared algorithm to calculate the edit distance between any string and any other string, okay? So that's a pretty straightforward, simple dynamic programming algorithm. But for this problem, we don't have two fixed strings. We have only one string, and we're trying to calculate all possible second strings and enumerate the ones that have a particular edit distance. So you notice how we did it row by row. This means that given a particular character and the previous row, we can calculate the new table row, okay? So we have a state machine that transitions from table row to table row based on character. Okay, and that's exactly the same as your elementary edit distance calculation. So what we do is we use a map from a vector of ints, which is my row, to a count, how many times that row can occur among all the possible strings of a given length. So we initialize our map with a single element that's got the entries 0 through n plus 1 if the initial string has n characters. And then for every length, for every single row in the map, we say, what are the possible characters? We calculate a new row for each possible character, and we accumulate it into a second hash map, and then we swap them. As we run, we walk through each row, and we find all the entries that are equal to D, and we accumulate those. So if we see a particular row can occur in 7 strings of length 3, and in that row there are 3 entries that have a value of D, then it's 3 times 7 is 21. We add 21 to our running total. That tells us there were 21 strings that had the edit distance of D, okay? There's an optimization you can perform that says any row values greater than D are equivalent. Once our edit distance gets to be greater than D, there's no operation that's going to decrease it. So we can saturate each entry at D plus 1 to help minimize the number of rows. And that's how you solve editing explosion.